nice to be here. It's my first Code Beam Berlin because I couldn't make it last year. I was on vacation. It was already booked. We are talking today about smart mapping of processes to nodes. And a warning before, it's work in progress. So it's not done yet. So why do we want that? So that's kind of like an overview of what we all want to achieve in our new IoT platform, Crisp.io. And in the middle, there is this thing that we actually want to kind of like decouple the whole distributed software design process from the decision making on which node you run it, because that's what you have to do today, and that's what it's the whole kind of like algorithms we are talking about today. Oh, sorry, that was leftover. Well, there's really free stuff, but that was from a different slide deck. So why do we want that? So the way IoT applications are built today, if they have cloud and edge and all kinds of device sizes, you make a decision beforehand what runs where, and then you write some IoT code, maybe in C on a very small, tiny sensor node. Then you have some Java code on a gateway. I just make it horrible on intention. Some Java code on a gateway that actually transfers everything to the cloud, and in the cloud maybe you want to do some machine learning, so you have some containers running Python, doing your machine learning things on GPUs, and then send back the information and make the decision on the edge. And you decide that, you build the parts, you have to build protocols, explicit protocols between the parts, and after you did all that, then you're basically stuck. Because if you then figure out, like, actually it would be good if you had this machine learning subpart already on the node, because then we didn't need so much data to transfer over there. But I mean, you're not totally stuck. You can rewrite everything, of course. But it's a big obstacle. There is an architectural lock-in that you have achieved there. Then you might find out, like, my intelligence on the edge is not intelligent enough. I might want to add more compute. So let's put a server in the corner. Then you need to kind of like pick up this server and make sure that your application can use that. And also it allows us to use all the capacity of all the small compute nodes we have at the edge. Because, I mean, let's say on our normal conveyor belt use case, we have hundreds of nodes which are not that big, 800 megahertz, but 100 cores at 800 megahertz is not nothing. So you want to use that. But for that, you also need to distribute your application in a very flexible way to these many nodes. So that's the thing you want to achieve, but it's not that easy. So maybe a little graphics. So we have a bunch of processes and a bunch of nodes. And the nodes have a non-fully connected mesh topology. So we have heterogeneous topology with like thin links and radio links and all kinds of links and different sizes of nodes. So they are all the same size here, but that's not the case. And then we have some messaging graph in our Erlang node that we know somehow. We will get to that, how we know that. And what we want to do is we want to automatically decide which process should run on which node to some optimization criterion. So what criteria are we thinking about? So some of the processes actually are just static. If I have the process that reads a sensor, well, it needs to be at the node where the sensor is connected to or has a connection to. So this one is fixed, and it actually makes our life a little bit more easy. We will get to that. Also, because that kind of like nails down the network a little bit in a few pinpoints, and that makes the rest of the optimization easier. Then we have latency, and network and compute bandwidth. Different links have different latencies, and latency and bandwidth actually have some additional complexity. So I will explain them a little bit on the next slide. Then, of course, memory usage. Not every node has a lot of memory, and some algorithms need a lot of memory. Some don't need memory at all, or almost no memory. Also, very important, energy. So we are doing a project, for example, with energy harvesting, where from a temperature gradient, so you can stick a sensor node to a hot device, and it powers itself by the heat. but you only get single-digit milliwatt, and you have to charge a capacitor, and you have to manage this charge to know when you can actually do some compute again. So but that's basically mainly bandwidth management, because you need to reduce the bandwidth, the compute bandwidth that you have on the node that you have available. But also the network is using a lot of energy. I mean, we usually ignore that, but I mean, there's all these papers about like how many CO2 is you're producing when you stream a Netflix film. But that I mean, this is like large scale, but it also works on smaller scales, especially on radio. And if you have like energy harvesting device, usually sends off its data via radio, because otherwise, why would you be energy harvesting? If you can run a cable to the device, you just power it by the cable. And this the radio energy basically is actually cannot be neglected. If you look, for example, at the extreme, if you have a space probe out at Mars or Jupiter, you need a substantial amount of your energy budget to send your radio data back home. So that's all energy usage also, and it's a thing that's very much looked at. So that's why we also look at that. And then we mentioned machine learning before. You have code that either requires a GPU, for example, or can run much faster on a GPU, because you might have can compile it like normally, and you can compile it for GPU. So you can make a decision like, if I put it on a node which has a GPU, everything would be much more efficient. And kind of like what our current project that also this research is funded by is caring about the whole security thing. IoT security is a thing. We are very much focused on this thing to get the IoT security done right. And one of the if you have a distributed network and you have the cloud and you don't own the cloud, so you might want to be careful what you want to put in the cloud. So you have sensitive sensor data, let's say 1 second 1 second resolution temperature reading of a room, which lets you determine how many people are in the room and if they are bodily active, which could be sensitive. And you might not want to leak this detailed data into the cloud, but for example, if you aggregate a lot of sensors and average them over hours, you might not care about it. Suddenly it's not sensitive anymore. So actually sensitive data can turn into non-sensitive data, also by encryption, of course. You encrypt it, then you can send it to the bad cloud, and as long as it's not decrypted there, everything is fine. But it's kind of like encryption is more a sensitivity compression algorithm, because you turn the sensitivity into this small key that you now have to take care of. And we want to also decide when mapping these processes to nodes that the user can flag in their distributed application which data is sensitive and which should not go in other places. So you have like trust zones, and you can flag the data and put it there. And we not only want to build this for Erlang processes, but of course, I mean, the reason I'm speaking here is we will make it so that for our ecosystem it will be the nicest. So we will have the most benefit of it. But I mean, yeah, we have these containers running machine learning, so we actually will extend it to all kinds of containerized, which is also a criterion, because like I can't run a container on a Crisp Nano board, for example. That doesn't fit. So you need to have the capability I can run containers. So basically, we build Kubernetes, but right, and in the language it should have been implemented in the first place. So short thing about latency, because we only talk about latency, and usually our diagrams between two processes, left process, right process, look like that. You have an arrow, and that's your kind of like the gap here is the latency. But the reality looks actually like that. It's actually a whole ribbon, and because the bits are not sent at the same time, you have a latency of the first bit, which is called the propagation delay. That's the thing, the speed limit of the universe. Is usually getting in the way here to get faster there. And then you have basically the serialization delay, which is kind of like the time for all the bits at the current bandwidth to be transmitted. So that means that the latency is dependent on the message size, of course. And we need to take this into account. So back to graphs. So we want to map graphs on graphs. So I was digging in the literature, like what algorithms exist to kind of like map one graph on another graph. And the only thing that I actually found is graph homomorphisms. Is basically a mapping between two graphs. That's what we are doing. And the only thing where there are real ready-made algorithms for is a graph retraction, which means you map a graph to a subgraph of itself. And we see that in this nice diagram on the right. We have this really gnarly graph here. I forgot the name of it. It has a name because it's an evil graph. It has lots of evil properties. And you map it basically to this inner circle, like this inner pentagram, where basically every edge is mapped onto an edge. And every node is on a node. So that for this graph it works, and there's algorithms for that, and there's a theory around that. I have no idea why this theory is needed. I didn't dig further because it didn't solve my problem. Because we have a different problem to solve. Because we have no problem that two nodes that have an edge between them are on the same node. That's actually nice to have, because then we have almost no bandwidth, almost infinite bandwidth. Only memory bandwidth is the limit, and no latency, or very little. And so what we need is basically is a generalized graph retraction that basically retracts because usually we have more processes than nodes. Because otherwise, I mean, if you have like 3 processes and 100 nodes, put them at any. It's probably fine. Oh, I'm hearing the other room. Oh, that's a little bit disturbing. What we want is to retract a larger graph of processes onto a smaller graph of nodes, and maybe also auto-insert nodes like a forwarding node, for example, or an encryption node. When we pass from a trust zone from a trusted zone to a less trusted zone, we want to automatically include an encryption node. The general complexity of that is NP complete. And the search space is n to the power of p. So n is the number of nodes and p is the number of processes. That's pretty large for any n and p. So the thing is, NP complete, usually people say, oh, you can't do that, it's NP complete, but there's useful solutions for NP complete problems galore, and most interesting problems are NP complete. So all the boring problems are not NP complete. But yeah, we will see that there's also limits to what you can achieve. So I looked at like, what algorithms do I use for that? How do I achieve that? Like I start in the middle, there's always these algorithms that I tend to go to when I'm stuck. So if it's very desperate, you use simulated annealing or genetic algorithms, because they work on anything. They converge slowly, but they will converge on anything that's kind of solvable at all. Simulated annealing is kind of like simulating the physics of cooling down a material, where when it's hot, then you can have like high jumps of energy, and while it cools down, kind of like it freezes into a pattern. So you anneal it, and you can do this with data and with processes and use the physics probabilities to actually do that. It's pretty useful. It's not very fast, but it basically solves everything, kind of. I mean, you never find an optimal solution, but you find a quite optimal solution. Genetic algorithms is basically you do mutations and you do crossover and then you do populations. Nice thing about genetic algorithms, they usually converge even slower than simulated annealing, but you can distribute them very easily because you can have populations of different nodes. You can run the algorithm distributed. That's nice. But kind of like the go-to things that I thought about first were SAT solvers. That's Boolean satisfiability solvers, which means you have a bunch of Boolean equations, and you're looking for Boolean values for all the variables in these equations that satisfy all the equations. That's what the SAT solver does. But when we look at that, we have lots of like numbers in this thing. Like we have values for like latency and all kinds of things, and we want to minimize and do something with these numbers. So that probably doesn't cut it quite to use a SAT solver. I mean, there is some theorem that you can map everything to a SAT solver, but that's not a useful mapping always. So there's an extension of SAT solvers, which is called SMT solvers, satisfiability modulo theory solvers. More details on that later, which is the first experiment I went with, basically. That's the thing you will see today. We will look at SMT solvers for this problem. And then there's linear programming and combination of the above. What's an SMT solver? It's basically an extension of a SAT solver, with some extra theories. So you have like Boolean equations, and you can have arithmetic equations or array equations or bit string equations. So there's extensions to this theory. And actually, I was very confused for a long time because I thought this modulo in the word has anything to do with the mathematical modulo, like integer modulo, like remainder at division. But it has nothing to do with that. It is just meaning modulo in the sense with respect to other theories. So we solve a Boolean equation with respect to other things. So that's what SMT solvers are. So further digging into that, there was one finding that there's a standard format for all these SMT solvers. It was actually created to run competitions on SMT solving. So there is a bunch of benchmarks, and every year there's a big competition who has the best SAT solver, SMT solver. By running it on all these benchmarks, and because everybody now can read this standardized format, you can actually compare the results, which is the one thing that brought them the most boost in performance gains of all the SMT solving in the last 15 years, because these benchmarks and the competition actually drove people forward. We have the advantage, we have like a simple way to actually define the problems, and then we don't have to kind of like a priori decide like which solver do we use, but because maybe the one solver is better at this than the other. We will see it, it's a Lisp-like syntax. It's a bit weird, but I'm slowly getting used to it. So that's kind of like the two big solvers. There's more smaller ones, so I didn't want to make a complete list. The most well-known are the C3 from Microsoft Research and CVC 4 or 5, depending on which version you take. Both are open source. C3 was closed source in the past, but they open sourced it later on. Even MIT license, industry friendly, very useful. And the C3 solver, that's the one that will be looking at a little bit closer, and that means it's demo time. So where are we with the time? Oh, yeah, so good. So out of the slides, into the demo. So is the code readable here in this window, or should I make it larger? Larger? Okay. Options. Default font. That large enough? It's a compromise, okay. So that's how SMTlib looks. Are we at the top of the file? Yeah. So it's a Lisp-like syntax, and you can declare a bunch of things. In this case, I declare a bunch of so-called consts, which are actually variables, which are actually functions. It's actually a const is a function with no argument, because it's all about like functions. So I declare a bunch of kind of like variables which are called const, which are of type int, and they're called sen, dm, r, and y, and we constrain the values on the letters in the asserts here below. Is that they need to be between 0 and 9. There's an additional constraint that m needs to be larger than 0 for a reason that you will just see, because we want to solve the puzzle is that they have the equation send plus more equals money, and you replace all the letters by a digit, then what's the solution for that? So we have an equation basically calculating these values with the thing, and then we do checksat, and because we not only want to see if it's satisfiable, because if you do checksat, it tells you either sat, like yeah, it's fine, or unsat, no, it can't, it's not fine, or don't know. That basically means I couldn't figure it out. So we extract the values, and in the sequence we're using it. So let's try it out. Where am I here? So I need to make this larger too, I guess. So we go more for an overlapping thing. Yes, this is in test. So we run C3 on money.smt. That's the file that you just saw. And what it does when you give it this file, it gives it a solution very quickly. hey, this works like magic. Let's see how far we can actually take it. So, next step, I formulated a subset of the problem of the overall mapping thing. So I didn't put all the criteria in because I first want to optimize the solving before I increase the criteria, because the search space doesn't grow by that. So let's look at that, how that looks. So that's a small example of the graph mapping. I won't explain everything here. No time, and it's also a little bit gnarly. So we declare some data types for nodes and procs. It's a little bit weirdly formatted because it's generated actually. And I have a bunch of functions like operational latency, which is like the latency of one operation on a node. Connection, is there a connection between these two nodes? That's how we encode our topology. Bit time, propagation delay, latency, we're actually not using that yet. I had enough problems without it. And basically the processes have like operations per run and the interval how often they want to run. That's just like an initial way of actually modeling the whole thing. And then the messages are also modeled here. And then we declare a func proc to node, which is actually the one we only declare that, and we specify conditions to that. But that's what the solver needs to give us. Like, how do we map the procs to the nodes? And then we have lots of values here. That's the adjacency matrix, who is connected to who. This is only 3 nodes on a chain. It's a very tiny example because as you see, you have to write a lot of things if you do that by hand. You have these latencies, so all these data is, and then you have lots of conditions like that a node is not overloaded. So basically, if P1 is running on N1 and the load of P1 on N1 would be that, and that the sum of all these should be less than 100%. And the load is a formula out of the values above. But yeah, details. So you see, you need to have a lot of like replicated code, because this is not a generalized programming language. You're specifying a problem, and while there is things like for all, this, do that, they don't always work with all theories. So you think, oh yeah, I just use a for all, and then it tells you, nah, I can't use a for all there. Sorry. I can only do it for this subcase. So it's kind of like a big landscape of things it can do and it can't do, which you need to explore. And in the end, basically, we check for satisfiability, and then we get the value. And because it's kind of like boring to run that, we do a little bit larger one, and that one we generate. So that is, it's called grasp.l. So we call the project grasp. So here we basically have Erlang code, so much more familiar than this weird Lisp stuff. And here we just describe these 2 graphs as digraphs. To check. As digraphs, digraph is a module that comes with OTP where you can describe arbitrary directed graphs. And we use that because it's useful. And then in the end, basically, we pass these 2 graphs into the generate function, which has lots of functions down there that generates the actual solver. So what do we do here? Let's make this also larger. So we have a... So we run Reba 3, we build it. And now we're building a ring example. So we... grasp. Oh, actually, I always forget which order. Yeah, this order. But we make it a little bit smaller. So what we do here is we have a ring of 5 nodes connected in ring shape, and a ring of 10 processes that should be mapped over there. Sounds very trivial, but for the solver, it's as complicated as any other graph. It doesn't help it at all. It's just easier for us to understand the result. If I would have used a random graph, we don't know if it's right. Here we can actually see if it's right. So we generate the ring example, which in this case generates, let me show you, this file, changed on disk, yeah. So there's a lot of these statements here. So this is all generated, basically, all these combinations. Pages of stuff, you don't want to handwrite that. And that's a common topic with SMT solvers. You generate the models and then you solve that. So let's see what C3 says to that. That's in a different directory. So in the end, I extract the process to node mapping and the load that the processes actually produce on these nodes. And we can see it actually nicely distributed it over the ring, not in a very obvious way, but you see that basically every node has 2 processes basically on it. And the processes that are connected also are neighboring nodes. So it picked a non-trivial result. It didn't just wrap it around twice, which is what I would have done. But yeah, there's other solutions for that we learned. Okay, so yeah, it worked. So back to the slides. So yeah, since I had this nice generation thing, let's run a benchmark. Oops. So 10 to 5, 0.1 second. 12 to 6, 2 seconds. All fine, all good. Then suddenly 14 to 7, a ring of 14 processes to 7 nodes, with my naive model, a bunch of 100 seconds. Then it's like, okay, if that is going up from 2 seconds to 200 seconds, this will. But then the next step still works. It's just 400 and something seconds. But then I went one step further and I couldn't wait for it. I waited 1.5 hours and it didn't converge. So that's why this error, I don't know how far this goes up, if it's centuries or millennia, I don't care actually. It needs to be faster if you want to have a useful tool. So yeah, I have a benchmark slide even. Made this morning. So yeah, obviously we need to optimize. So learning number 1, a naive SMT model that we can understand very easily doesn't scale well in this case. Then remember the sensors and the actuators. So as soon as you start, I don't have an example for that, but as soon as you start pinning a few processes on nodes, like our sensor, it's much faster. Because what we are doing now, we kind of like, it has full degree of freedom. We can map this ring in any way it wants. And there's so many solutions it actually needs to choose from. So it actually, I've seen that if you pin down a few processes, it actually converges much faster because you reduce the degree of freedom greatly. So currently we just used functions as theory for the node mapping, but there's other theories like arrays. Arrays are very useful for graphs because you can make the matrix, you can actually encode it as an array with indices and everything, and it might be a little bit more compact and faster. So next experiment. And then also there is functions called PBLE and PBGT, which means it's a weighted Boolean sum. So you have a vector of Booleans, variables, and you have a weight in front of each. So you multiply it with a weight. When it's 1, when it's true, it's 1. And you basically say, PBLE would be say, if this weights with this binary vector is smaller than a value, less than or equal, smaller than or equal. That is a thing that the solver can work much faster with. So that would be a next thing to explore. So there's still a lot of work ahead to find a real good solution. And you can tweak the solver. So I just run C3 in the default mode, but there's a lot of tactics that you can actually switch on and off and do all kinds of things with to actually tweak it for specific problems. So now I'm basically beyond the beginner mode that I understand how SMT works and how you model it, but I have no idea how it works actually, because now the fun starts. So now trying to get an expert in the next year, till the next talk maybe. And also there's other ways when we hit an obstacle, we can divide and conquer. So for example, you have these graphs, they are not structureless usually. So they have lumps in it. So you kind of like find the connected subcomponents of the graph, which are very interconnected, and model them as one node, and then have a smaller problem to solve, and you can iterate on that. So you go down until you have a small enough problem that the SMT solver can solve, and then you go backwards and make the big picture. So there's basically generally, currently we are not using the structure of the problem at all. So we're not using the fact that we are actually mapping graph to graph and that this is graph algorithms and all kinds of things. Actually, how do we actually run this from Erlang? So currently we just generated the source file, but that is actually not that nice. So you probably can't read that. But what you see here is the example, with a little bit omission here, of the send more money thing, but written as Erlang tuples. Why is it written as Erlang tuples? Because somebody is actually building this into OTP. So thanks to John Hogberg, who wants to validate optimization phases of the compiler with SMT solvers, it's actually landing an OTP in its own library. And we have used that. So this is actually an actual run that Luca did with John's branch where the SMT solver is in. We couldn't quite get the result out. So you see only, down here, you would see only SAT. And the get model was ignored because it's not implemented yet. So we kind of like now have to expand the NIFs that John already built to have that. So this is something that everybody will probably be able to use next year, in next version of OTP, I guess. Which is, yeah, thanks to John. And also thanks to John for actually introducing me into SMT solving. Happened at Erlang Workshop, very useful to go there. You learn lots of things. Little plug on Erlang Workshop also. What other further work, despite optimizing it to scale it up? Because what I want to achieve is that we can map, let's say, 1,000 processes to a few hundred nodes. I mean, 100 nodes is good. I mean, once we're managing projects with more than 100 nodes, is a luxury problem for us. So yeah, we will cross the bridge when we get there. So sometimes you can't map it in a way that everybody can reach everybody. So you need to insert a forwarder if you have a not fully connected mesh. So that can be actually very easily modeled. I did a very small example on that. I can't show it, no time. You can make the solver that, like, if you can't find a way, then insert a node, basically. Then there's also specific nodes like aggregation or dissemination, like spreading out information or collecting information, which has an implicit way to kind of like spawn itself into multiple things. So you aggregate some data, and then if you have, like, the topology doesn't let you, you pre-aggregate something further out, and then you aggregate further down, and you build a tree, basically. That can be also done automatically. And also we want to auto-scale the process network, like that we have something where for every sensor you want to have a certain process running, and then you want to have aggregation running, and then you build a digital twin, and then you want to push out the data from the digital twin to the edge to actually do some decision making there. And of course we want to integrate it into GrisBio to make it into a useful tool, which is currently it's not. Currently it's work in progress and we are experimenting. So we have two little problems that I didn't speak about. How do we actually know the node topology? Well, one way is if you build it yourself, for example, with Spray, the thing that we built, with Spray you can specify an arbitrary topology in a file, and it generates distributed Erlang nodes with encryption and everything, and takes care of all the key management and everything. So the features are all on the slides. Currently, it does it on fly.io. But it would we extend it to all kinds of clouds. And if you build your topology with that, you already know the topology because you configured it. And one thing we are working on currently is we want to extend Braid to the edge, so that you have basically that you can build this topology, your edge cloud, and then have gateways. And Crisp Nano is the next hardware we're building, by the way. The smallest full-blown Erlang node without reduced instruction set on the planet, we hope. Or at least the most power conserving, because there's this energy harvesting project that we need to solve. So the next problem in Erlang, we don't know normally which process talks to which process. So how do we learn the process topology? There's several short ways to do that. One is there's a set of patterns that come again and again. So what we can build is we can build libraries for these patterns. We have like aggregation, we have dissemination, we have request response, very easy, or we have a static data flow in the corner that we have like some data flow thing that always is the same pattern, which is also very common in IoT, or you have some map reduce or expand and collect again. Or the inverse also exists, basically. If you have a digital twin, you first need to aggregate all your sensor data to a digital twin, and then you disseminate back the results of the digital twin so everybody knows the state of everything. That also exists. I need to add it to this slide. There's another way. Basically, if you pre-specify your topology in your application, then you know who's talking to who. And that is actually a diagram from a PLC programming language. A diagram from a PLC programming language where who knows what a PLC is? Okay, PLCs are the computers that we don't program normally. There's a whole set of programmers programming PLC, and they run everywhere from everything from a garage door opener to a whole factory. So and they like dataflow, and they have these languages with this dataflow thing, and we actually built a compiler for Erlang for that. So we compiled this on the beam, so we can actually have an offer for the PLC language programmers to get back. But currently we're looking at that because if you look at it closer, then you have all these wires running around. The thing in the top is events happening, and the thing at the bottom is just data. And the data is aligned with events. There's normally lines here. They connect that here that says which data is actually synchronized with which event. But so you have the whole data flow of the whole application here. And when we implement that in Erlang, because we need to implement some function blocks, they're called function blocks, in Erlang, that looks actually like that. So let's look at the E delay, because that's one we can't implement in the language. That's how it looks like Erlang. How does it start? Behavior, PLCF block. And it has an init and a state record and a handle in event where it has start and stop. And basically it sets a timer. It's a delay basically. You can set the delay value here. And basically after this delay, it will trigger this event. So when the timer triggers, when the timeout happens, we're actually sending the out event. So this is maybe not nice enough, but we could actually turn this into a bunch of behaviors, which lets you build your IoT application in Erlang or Elixir, or LFE, or Gleam, or whatever. Well, Gleam, I don't know. You probably have to re-implement it with type checking. And build your application and plug it together with these building blocks. Maybe we use a different graphic so you don't get confused and think you're PLC programmers now, or something like that. But that is also a way to know beforehand what the communication topology looks like. We will integrate that into Grisp.io. Actually try it out. It's actually open and you can do things, especially when you have a Grisp board, which was the little pop-up that I forgot to remove before. And that is the end of my talk. The talk was, I need to mention the EU because they pay for this whole thing. So this was done under this Rescale project, which is also doing great things, or hopefully great things, for software supply chain security of the Erlang ecosystem. So we try to get a bunch of tools out of this project too, but what I'm talking about today is also funded by that project because there's this whole data sensitivity trust thingy, this one criterion, but for that I also need a mapper. Okay, do we have time for questions still? Or did I use all the time?
Yeah, I think we have time for one or two quick questions. So raise your hand if you do have a question. And if not, then I'm going to read one from the Huva app. Are there any parts of the project that could benefit the Nerves ecosystem and vice versa?
Sure, it would run on Nerves.
Okay.
It's not tied to any way of operating system. It would run everywhere. It's just the Erlang or Elixir code, basically.
Okay, cool. We have one more question.
With the scaling issues in the current approach and mentioning divide and conquer, you could maybe also on the side of the processes apply some cluster algorithms which basically cluster the nodes into the clusters which equal the number of hardware nodes, and then you only have the problem of one-to-one mapping.
Yeah, well, like cluster both nodes maybe, and you can also play with different strategies. You just run the solver with different strategies, and then see what fits, and you run it in parallel, and you let it try thing, because that's what it does internally too. It tries a lot of strategies to actually solve the thing, and currently I'm not guiding it at all. So this just started to run this morning. So yeah, I did the benchmark at 11. So I'm not concerned at all about scalability. This is like, expected outcome.